So today we're covering two sections, 5.4 and 5.5, and we're going to talk about something called a definite integral and the fundamental theorem of calculus. What? That sounds important, right? It's the fundamental theorem. And it took you like 3/4 of the way into the course to get to it. But we're going to learn the fundamental theorem of calculus today. So up until now, we've been thinking about integrals as undoing a derivative, right? We've been thinking about them this way. Whereas if you have a derivative and then you write your little bookend notation, that notation is telling us to like work backwards, and then you get the original function back. So that's one way to think about an integral. But there's another way to think about it, and that's area under a curve. So we're going to explore this idea of an area under a curve. Now, a straight line can be a curve. So that's just a term they give when you graph something. It's called the curve, and you're going to look under it. So even if it's a straight line, they're going to call it a curve. But we're going to look at some examples we can do with just straight up geometry that you already know. So let's look at example 1. If I wanted to find this shaded area between x equals 0 and x equals 3 under the curve, this constant function 3, if I wanted to find that area, we can just use geometry, right? We have a formula that finds the area of a rectangle. We know this is the area of a rectangle, and that's just going to be length times width. Okay, so let's just find that real quick. So this area, it's going to have a length of 1, 2, 3, a length of 3, and a width of 1, 2, 3, a width of 3. So this area is just going to be 9 square units, whatever we're measuring by. So straight up geometry. You could have also just counted the squares inside the shape, right? There are 1, 2, 3, 4, 5, 6, 7, 8, 9 square units in there. So you could have just counted that up. So I don't need calculus to do this problem. I have geometry for this, right? Same thing on number 2. Let's look at example 2 here. This is a rectangle, and we have a formula for that, right? Area, sorry, not a rectangle, it's a triangle. Area of a triangle. So you might have this memorized. It's 1/2 base times height. Basically, you're just finding the area of the rectangle and you're cutting it in half, right? And instead of length times width, they're calling it a base and a height. So that's where that formula came from geometry. So let's just go ahead and find that real quick. So my base is 1, 2, 3, and my height is 1, 2, 3. So this area would be 1/2, 3 times 3. So if you multiply all that together, half of 9 is 4.5 square units. Cool. And again, you could have just counted inside that shaded region and found the number of squares, right? Let's go ahead and count it. So we have 1, 2, 3. And then these two triangles would make piece number 4. And then we'd have half a piece there. So 4.5 units. Okay, so show me a status real quick, how you feel about finding the area of that shaded region using geometry. How are you feeling about that? Okay, so that's been great. Now let's try this problem down here. Now I've graphed a quadratic. Before I was graphing linear functions. Now I'm graphing a polynomial, a quadratic function. It's making this curved line here. And then I'm wanting to find the shaded area, again, from 0 to 3. We're sticking with this 0 to 3 thing. But now it's like, how? What? Does anyone have a formula for this off the top of their head? I don't. This isn't a standard shape that we're used to, right? It's not a rectangle. It's not a triangle. It's not even a trapezoid. It doesn't have straight sides, right? It has these curved sides. So we don't have a standard formula for this. But there's some things we can do to estimate the area under this curve. And there's lots of different methods we can use. We're going to look at one of them today. I'm going to look at one of these methods. Does anyone have any idea? If you've taken calculus before, don't say it, but anyone have an idea of how I could estimate the area under this curve? There's lots of ways. No. You know, we could count the squares, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you could be like, this piece kind of goes with this one. That could be 10. And I don't know, maybe this would be 11, and then maybe some more. I don't know. See, that's not very accurate, trying to count the squares under there. So what we're going to do is we're going to break this shape into smaller shapes that we know a formula for. And the shape we're going to use today is going to be a rectangle. So we're going to break this shape up into smaller rectangles that we can calculate, and we're going to try to estimate the area. So I'm going to do that on the next page. Okay. We're going to approximate the area under this curve with 3 rectangles. And I'm just picking 3 arbitrarily because for sake of time, we're going to use 3 rectangles. I could just do one big rectangle, right? Like I could say, okay, let's enclose this in one big rectangle. And then I could say, okay, that's a base of 3 and a height of 1, 2, 3, 4, 5. And I could say, okay, the area is approximately 3 times 5. So the area would be approximately 15. But that's not a very good estimate because we have all this like white space that got counted that isn't really part of my shaded area. So 1 rectangle is not a super good estimate. So what I'm going to do is just use 3 rectangles. So let's go ahead and try 3 rectangles here. And my erase feature is not working. There it goes. Okay. So we're going to try 3 rectangles. I have a space from 0 to 3, and I'm going to break it up into 3 rectangles. 1, I'm drawing the bases right now. 2, 3. And there's 2 ways we can draw these rectangles. So right now we're going to draw something called a left rectangle. So we're going from 0 to 3 using left rectangles. What that's going to do is you're going to take the bottom left-hand corner, so we're on the left, and you're going to go up until you hit the curve. So right there at 4. So the height of the rectangle is going to be dictated by the left corner. And then I close it off, and I calculate the area of this one rectangle. So that's going to be a 1 by 4. So when I go to find the area, I'm going to have a 1 by 4 rectangle. So that's an area of 4 plus, and I just keep doing that. I keep drawing rectangles where I start at the left corner and I go up, 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 boom, till I hit my curve. And I close it off. And then, so this would be a 1 by 5 rectangle. So I'm going to add that on. Okay, and then we'll do one more rectangle. I'm going to start here at the left. I'm going to go up, 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 boom, till I hit my curve, come down. And this would be a 1 by 4 again. Okay, and when I add all these up, that'll be my approximate area. So I used 3 subintervals. That means I had 3 rectangles, right? And I used left rectangles. The height of the rectangle was dictated by that left corner there, and I got this estimate. But see all this white space that got counted that's not really part? I mean, this is probably an overestimate, probably, right? Because there's so much white space that's being left over there. So this is probably an overestimate, I'm guessing. There is some space here that might balance some of it out, right? There's some purple space that didn't get counted, but there's a lot of white space that did get counted. So I don't know. I'm going to guess that this is probably an overestimate. Okay, now we're going to repeat this process, but we are going to use right rectangles this time. Okay, so same process, but we're going to use right rectangles. Still going to go from 0 to 3. So I'm still going to go from 0 to 3. I'm still going to break it up into 3 rectangles. But now we're going to do right rectangles. So let's do our bases here. I'm going to have 1, 2, 3 rectangles. Okay. But now I'm going to go to the right-hand corner, go up, 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 till I hit my curve, and then close it out. So this would be a 1 by 5 when I find this area. That'd be 5 plus. Okay, let's keep going. So I'm coming here to the right. Boom, right there. So that would be a 1 by 4. Oh man, we have one more. So this one, remember, you start at the right corner, you go up, and I hit my graph right there. Oh my goodness, this is a really short one. This is just a 1 by 1. So if I add all that together, that's probably definitely an underestimate, right? Because I have, look at all that purple space that wasn't counted. So this is definitely an underestimate. Okay, show me a status on what we've done so far with breaking this area into rectangles to get these estimates. And you can also, if you've, Google this, they sometimes use trapezoids. There's other shapes you can use. I just used rectangles. Okay, now these weren't very good estimates. I mean, one was an overestimate, one was a really big underestimate. Any ideas what I could do, still using rectangles, but any idea on what I could do with the rectangles to make this more accurate? Ooh, that's a good idea. If you have an overestimate and you have an underestimate, you could average them. That's cool. That would be a really horrible function to for later if I'm thinking ahead, but that would work. Any other ideas? Well, what about this? Did I have to use 3 rectangles? No, I could have used 1, right? But 1 was even worse. Remember when I tried 1, it was 15 square units. So I picked 3, but what if I had chosen more? So I'm going to come over here to this one I haven't written on yet. You don't have to write this down. But what if I chose 6 rectangles? Instead of, let's see. So you don't have to write this down because I'm going to show you on Desmos in a minute. But I arbitrarily chose 1, 2, 3 rectangles. But what if I cut those in half? And now I'm going to use 6 rectangles. And I'm just going to go from the left. So if I did that, what would that look like? So I would go up 1, cut over half, start on the left, go up, cut over, down, start on the left, go up, hit my graph, over, come down, start on the left, go up, hit my graph, come down, start on the left, go up, hit my graph, come down. What's happening to my estimate? Yeah, compared to before, I'm wasting less space. And I know that's kind of hard to see with what I drew, so I have Desmos for you. So there's a link there built into your notes. If you have them open on your screen, you can click it, or you can just follow along with me real quick. But I'm going to show you this idea of using more and more rectangles. So let me share my screen real quick. Oops. Okay. And here is Desmos. And what I've done is I've, well, let me move that over. Okay. So I've programmed Desmos in here. I graphed that function that the parabola negative x squared plus 2x plus 4. Here was my 3 rectangles. They're touching on the left. They're touching on the left. So I had a area of 4, an area of 5, and an area of 4, just like we did before. But I have these sliders here, which are going to help me break these triangles up to more and more triangles. So rectangles, more and more rectangles. So right now, ignore all this scary stuff. Right now I have it set at 3 rectangles. But what if I did 4, 5, 6? See how there's less and less wasted space the more and more rectangles I do? So the skinnier the rectangles, the less wasted space there is. I'm at 40 rectangles right now. Now I'm at 50. I'm going more and more. So the more and more rectangles I can draw, the closer and closer it is to that actual shaded area with no wasted space. That's 100 rectangles. You can hardly see any of the wasted space. I mean, if I zoomed in really close, you can still see there's some wasted space there. But what if I did 500 rectangles? 1,000,000 rectangles? See how you would get less and less wasted space there? So this is kind of like, you know, those ideas of limits, doing an infinite number, getting infinitely close to something. If I made these rectangles like infinitely skinny, like so skinny, it would really approximate or hug this curve. And now no one would actually do 100 rectangles by hand, right? But I just wanted you to see this idea. We can use technology to see that we're getting less and less wasted space to where essentially it's going to be the shaded area there. Okay. Before I go on to connect this to the next idea, are there any questions about this idea of the more rectangles you use, the better it approximates that shaded area, the better it hugs the curve there? How are we feeling with that idea? Feeling okay? Show me a status. You're like, I don't even know what just happened. Okay, so, I need to share the notes again. That's not it. Uh-oh. Here it is. Okay. Let me put this over here. Okay, so let's think about this idea of rectangles. So what's something we could do to make it more accurate? So one, we said take the average, but also use more rectangles. Use more rectangles. Use more rectangles. Well, another thing we could do is use calculus. We can use calculus. Okay, so let's talk about this idea of a definite integral. We're going to use calculus. So the integral is going to look like you're used to seeing. It's going to have the bookends, this S-shaped symbol and the dx, and then you're going to have a function in the middle. But now you're going to see 2 numbers on that integral. We're going to do something with those. You're going to see these 2 numbers on the integral. That's how we were going from 0 to 3 earlier. Now we're going to go from A to B. And we have this rule in calculus. It says if I take this integral and I start adding in these specific starting points and ending points, it's going to approximate the area. And this is a non-STEM calculus course. So in a real calculus course, we'd go through all kinds of proofs and we'd jump into the beauty of this and, we'd see some theorems and it'd be beautiful. But in this class, we're just going to get a main idea going on here. Okay, so let me jump back over here and let's just talk about this main idea. Let me jump to one I haven't written too much on. Let me come over here because I can erase this one easier. Okay, so here's the idea that we're going to see. Okay, we're going to see this notation, and then your function is going to be in the middle. So this function that we had here, that's going to be our function that goes in the middle. Dx. And then since we were going from 0 to 3 as my interval, remember x started at 0 and then x went to 3, you're going to see those numbers written on your integral right there. And then this is how we're going to read the notation. Let's think about what f of x is telling us. F of x is the height of the graph, right? If you put an input into x, it calculates the height of the graph. If I put an input in there, then this calculates the height of the graph. It's your output. So for example, if I put x equals 0 into my function, it goes up here. F of 0 has a height of 4. And when I'm making the rectangle, that was the height of my rectangle, right? So this is going to like calculate the height of your rectangle. And then remember d of x, that's a way of saying like the change in the x value. So this is like saying change in x. Well, the change in your x coordinates, that's your width, right? That's just the width of the rectangle. So this is like the width of your rectangle. So this calculation is like doing the height, the length of the rectangle, and the width of the rectangle. So it's calculating the area of a rectangle. And then what your other notation is doing with the 0 and the 3 is telling you how many rectangles you're going to be the x interval that you're going to be looking over. And then the summation is like you're breaking it into an infinite number of rectangles. So think about this notation as like a summation. If you've had other pre-calc classes, you might have seen this for summation. But this S, I think about this S-shaped curve is like another way to say summation. You're just adding up all the rectangles, basically, is what this is doing. So that's our big overarching idea to the notation. We're just basically finding the length and width of a rectangle, and we're adding them all up over a certain interval. So let's see this in action. So let me pop back over here. Sorry, I will have to organize these better for online. Okay, so there's all this stuff I'm going to talk to you about. But we're just going to see it with problems we're comfortable with first. So here we go. Let's look at number 1. We already know the answer to this. We already found that the area was 9 square units, right? We already did this using just straight up geometry. Now we're going to do it with calculus. So what would my function look like? So I'm going to take the integral of the function over what x interval? From 0 till I go to 3. So I'm going to put 0 to 3 there. So I'm just setting up my notation. Now I'm going to replace that f of x with the actual rule. Now this was a constant function. It was linear, but it was the constant function. When I had an f of x, no matter what I input, the output's always a 3. So I'm going to replace this f of x with a 3 because that was my function rule. Okay, now we're going to find the integral. Ignore these numbers real quick. Just find the integral like you normally would. Find the antiderivative like you normally would. So if it helps you to write in the x to the 0 power so you can do your reverse power rule, go ahead and do that. So let's do our reverse power rule. So that would be 3x to the 0 plus 1 over 0 plus 1 plus c. Okay, so that would be 3x to the first over 1 plus c. Oops. So that would just be 3x plus c. Just normal everyday integral you've been doing. Now, what we've actually calculated here, y'all, is the area of a rectangle function. So the height of this rectangle is always 3, right? Height is always 3. So this is the height of my rectangle. The 3 there is like the height of my rectangle. And then the x, the width of my rectangle, changes based on how many rectangles I cut it up into, right? So this is like the width of my rectangle. So see how we created the formula, length times width, or in this case, height times width? We created that formula. We have a variable in there because I could break it into 3 rectangles. I could break it into 6 rectangles. I could break it into 100 rectangles. We just created that right there. And what we're going to do, though, is go back and use these things I marked out. Oops. These things I marked out. So let's unmark those out. We're going to go back and use these, and this is where our theorem comes in. It says we're going to plug in a 0 and a 3. So we use this notation where instead of this squiggly thing, the squiggly thing goes away because we've done the antiderivative, right? We did the reverse power rule. So squiggly goes away, bookend goes away. They go away, they've done their job. But we replace it with a stick at the back that says we're going from x goes to 0 to x goes to 3. So we're replacing it with this stick because we still have to show that specific interval. Okay, and what are we going to do with those numbers? We're going to plug them in and we're going to subtract. So this is where that theorem that's typed up here, this is where this theorem comes in. Okay, the theorem is saying you plug in the A, you plug in the B, and then you subtract them. But order is important in subtraction, right? So let me come over here to this theorem real quick and talk about the order. So see how there's a B and an A? Those are called your limits of integration. So I'm going to label those real quick. This is called your upper limit. Now these are different than limits that we did back on test 1. This is the upper limit of integration. And the other one's called your lower limit. And order is important in subtraction. So when I look at my theorem here, it says plug in the upper limit first. So first I'm going to plug in the upper. Then I plug in my lower limit second. And then I'm going to subtract them. So let's go ahead and do that. I better get the answer 9 out because I know that's what the area is. So hopefully we get the answer 9. Okay, so one time I'm going to plug in the upper limit. One time I'm going to plug in the lower limit, and then I'm going to subtract them. So my upper limit was a 3. My lower limit was a 0. And I don't need that plus c anymore because you don't have to write this down. But let me just show you what happens. If I take all of this, 3x plus c, and I plug in my upper limit, minus 3x plus c, and I plug in my lower limit, 0, what's going to happen to those c's? Let's see what happens to them. So I'm going to end up with 9 plus c, then I need to subtract 3 times 0 is 0, and then I need to subtract c. See how the c's are just going to cancel each other out? So we do not really need to write that plus c if you have a definite integral. If they give you numbers to plug in, that's a definite integral, then we don't need the plus c because it's not generic, right? We have these specific numbers we're looking at. So we don't need the plus c. You can write it and they'll just subtract off later, but it just makes it a little bit yuckier. So if I don't have the plus c, look how much nicer it is. If I don't have that plus c, then I'm just going to have a 3x. So I'm going to have a 3x minus a 3x, and one time the x is a 3 and one time the x is a 0, which is way nicer. So I get 9 minus 0, which was 9, and that's what the area is supposed to be, right? That's the area under the curve. This is the shaded area. Now, would I ever use calculus to find this shaded area? Heck no, I would use geometry or just count the squares, right? Like, no one would actually use calculus to, well, I shouldn't say no one, but you probably won't actually use calculus to find this area, but I wanted to show you that the calculus worked. Calculus works here. And I know this idea is new, but it's piggybacking on your old antiderivative rules, your reverse power rule, your reverse e to the x rule, your reverse element of the x rule. Now we just have this extra step of plugging things in and subtracting. That's the only new thing for today. So let's try another one, and then another one that we know, and then we'll try the harder one that we were doing those estimates for. Okay, so let's look at this one that we know over here. Got to set up our integral. Okay, so I'm going to do the integral of f of x dx from a to b. That's like my generic template, right? Okay, well, what's my rule on this one? So the thing that was graphed, so linear function, slope of 1, y-intercept of 0, that's just your identity function. So I'm going to replace, oh, instead of an f of x, they used a g, but you know, the function can be anything. So I'm going to replace that g of x with the rule x. Okay. And then my limits of integration went from 0 to 3 again. So I'm going to replace my limits of integration with a 0 and a 3. So it'll look like this. 0 to 3 x dx. Okay, now you just find the antiderivative following your reverse power rule. There's an understood exponent of 1 on this. So my reverse power rule would be x 1 plus 1 over 1 plus 1. And I don't have to write the plus c anymore because I'm replacing it with the 0 to 3. Okay. So that would give me an x squared over 2 from 0 to 3. And y'all, that's just the area of a rectangle. I'm sorry, God, triangle. That's just the area of a triangle. Isn't it just 1/2 base times height? But my base is an x and my height is an x, because they're the same thing here. If my base is 3, my height is 3. So if my base is x, my height is x. So if I multiply 1/2 times x, I get x squared over 2. It's just, all we've done is we've used calculus to create the area of a triangle. But if you don't see that, that's okay, because the calculus will do the work for you, right? So let's just keep doing the work with the calculus. Now I'm going to plug in my numbers. So one time I'm going to have x squared over 2, and I'm going to plug a 3 in. Minus, I'm going to have an x squared over 2, and I'm going to plug a 0 in. And let's see what we get. Hopefully it comes out to 4.5. Okay, so when I do that, I'm going to get 9 over 2 minus 0 over 2. So that's just 9 over 2, which is 4.5. That's the shaded area. So let me pause for a minute, give you a chance to think of a question or ask a question. How are we feeling on this idea of plugging in that x interval to calculate this area under a on this one? So remember this one, that was that parabola that we were just having to do like overestimates or underestimates as best we could. We did it with 3 rectangles. Now we're going to get the exact answer. So the integral, this integration, since it's kind of like a limit, it's saying like we're going to add up like an infinite number of rectangles. This is your exact area under the curve. It's not going to be an estimate. Okay. So they're taking this, they're still taking the region from 0 to 3, but they're breaking it into like an infinite number of rectangles. Okay. So what would this look like? Well, let's follow our rules here. I already have it set up. Here was my original function. I have my lower limit and my upper limit. Okay, so we have to take the integral. And if it helps, you know, for your previous sections, you broke this up into 3 different integrals, if that helps you, because they could follow 3 different rules. All of these happen to be reverse power rule. But if it helps you to split it up into 3 different integrals, so there might be 3 different rules to follow, that's totally fine. Or you can do it all at once. I'm going to split it up into 3 different integrals because that's what your help tools will do on MyMathLab. And I'm just going to reverse every single one following my reverse power rule in this case. So, okay, so this one would be negative x 2 plus 1 over 2 plus 1. And again, you do not write the plus c because we're going to go over a specific region. Okay, so that's going to be a negative x to the 3rd over 3 between these numbers. So let's go ahead and do that one. So one time I'm going to plug in a 3 minus, now be careful on this one. This one's tricky because there's a subtraction built into the formula and there's a negative built into your integrin, right? So you're going to end up with a double negative. So be really careful. It's a negative x cubed over 3. I just happen to be subtracting them because that's what my theorem tells me. So let's get all that in our calculator and see what we end up with for this one. Let's shrink it up a little bit. So that is going to be negative 9. Negative 9 minus 0. Plus 0. Double negative would make it, well, it doesn't matter. Minus 0 plus 0. And I just have to repeat that process for all of these pieces. So right now, I've only done this first piece, and I got these 2 numbers. And I'm just going to keep going. Now let's do this next one. Okay, reverse power rule. This one's being added. Okay, nice. So that's going to be an understood 1 there. So 2x to the 1 plus 1 over 1 plus 1. And I'm not going to do a plus c. I'm going to go from 0 to 3. Okay, so that's going to be a 2x squared over 2 from 0 to 3. Ooh, the 2's divide out. That's nice. So I just have x squared. So one time I'm going to do, and these are both being added. Now that's important because if it was subtraction, you'd have to distribute, right? But it's adding. So I'm going to have an x squared minus an x squared, and one time I plug in a 3 and one time I plug in a 0. So I'm going to add a 9 minus 0. And again, since that's being added, you don't have to worry about distributing the subtraction. If that had been subtracted, you would. But it's being added. So just be really careful with your signs, just like you would in any normal algebra problem. So it's being added, so we don't need to distribute. Okay? And then we just got to go. So now we've done this middle one. Now we'll do the last one. I'm going to be quiet and let you do the last one on your own. Okay, I got 12 and 0. Okay, so when we add all this up, let's see. Oh, our 9s have a -9 and a +9, so they're going to add to 0, and then the zeros aren't really there. So all of this is just 12? Okay, and that makes sense because remember our underestimate was a 10, I think, and our overestimate was a 13 or something. So 12 makes sense, is the area, the exact area. And if you play with that Desmos thing, if you did like, 1,000 rectangles, it would get really close to 12. Oh man, that hurt my brain because I do it a different way than my math lab. That was a lot of algebra and it's very messy. Oh my goodness. That was a messy mess. But since we're using my math lab for homework, I'm trying to use the textbook methods. So when you see help on my math lab, it looks like what we've done in class. So cool. It was between 12. Wait, I have to go back and peek because now I don't remember. That really weird one. Yeah. It was 13 for the overestimate and 10 for the under. So 12 being right, this one was a closer estimate anyway, and 12 was closer to 13. Okay, that makes sense. Okay. I know this looks like a lot of stuff. Do y'all want to know the super amazing great news? Okay, here's the super amazing great news. I have to test that you can do this process. So on your homework, you are going to practice this process by hand over and over and over and over because it will be on your test. However, once we do word problems and things like that, you can use technology to do this for you. What? You can use Desmos, you can use a graphing calculator, because these are very time consuming. Like this took us a lot of time. So I would hate to embed this into a word problem, which already takes time, right? So you're going to get to use technology to do this. So for test 4, you will either have to use Desmos or a graphing calculator. I don't care which one, but you have to use one of them. You do not want to take your test without technology because you will never finish. You will just go forever and ever and ever. Okay, so I'm going to show you how to do this problem with technology. Right, if you have a graphing calculator, grab it. If you want to open up Desmos real quick, go ahead. So let me just write really big before I even do this. I'm going to write big on here. You will have to do one by hand on the test. So practice. So you will have to do one of these by hand on the test. So practice. Underline, underline, underline. Smiley face, hearts. But let's do it with some technology. Oh, and there are these properties down here that I'm just going to introduce them as we need them. So don't panic too much. For sake of time, I'm going to but some of them, let's just look at number 3 real quick. Because number 3 is very similar to something you've seen. Number 3 is just saying if there's a constant, you can pull it out to the front, even though you have those limits of integration. You can pull it out to the front. So that's something that we've seen. It's also saying if you have two terms or 3 terms being added, you can split it up into separate integrals. We just did that. So those are the 2 we need for today. These other ones I'll sprinkle in as we need them. So don't panic too much. Number 1 is kind of self-explanatory if we go look at it real quick. It's just if you're plugging in the same limits of integration and you're subtracting, of course the area is going to be 0. So keep that in mind. And then 2 is just saying if you switch the order of the limits. So what happens when you switch the order of subtraction? It just changes the sign, right? If I do 5 minus 3, I get positive 2. But if I do 3 minus 5, I get negative 2. So basically just be really careful with those limits of integration and the order you're putting them in. But anywho, we'll talk more about these as we need to. Let's talk about technology. So I'm going to show you with Desmos. So I'm going to go through these steps here with Desmos. I'm not going to go through the steps with a calculator, but I wrote them down. Here, some of them are really self-explanatory on a calculator, and it'll just straight up type the notation for you. But if you have an older one, you have to interpret the order, and I can help you with the graphing calculator on like a individual basis or in office hours, because I just realized I can't, like in class I have a document camera and I just put my calculator up under it, and I can't really do that here. So let's just go to Desmos, and we're going to get this answer 12 using our Desmos. What I have to come back up here. Let me write down what this function was. It was negative x squared plus 2x plus 4. Okay, so let me go to Desmos. Oh, I need to share that with y'all. Hold on. Here it goes. Okay, so let me open a new tab here on Desmos. Okay, open up the graphing calculator. Okay, let me type in, so I'm going to type in my function. Okay, so this was our little guy there. Oops. Okay, cool. And look how easy this is to calculate on Desmos. Are you ready? So when you're in that line, hit enter to open up a new line. And then you're going to come down to the bottom right-hand corner. You should see a little, like your keyboard symbols. Oops. Hold on. Something weird just happened. There it goes. Oh, weird. Okay, so from your keyboard, when you click that little keyboard down on the bottom left corner, you'll see functions as one of the options on the keyboard. So click functions, and it'll pull up a menu. So there's a trig menu. This is not a trig-based course. There's a stats menu. There's a dist menu. Is that distance? What is that? Oh, distributions. Oh, God, I didn't even know that. That's so cool. And there's a miscellaneous one. So go to miscellaneous. And we want to do our integral. So let's click integral. And when I click the integral, it automatically does a definite integral. So see how there's a little blinking cursor for my lower limit, which was 0. And then I'll click up here for my upper limit, which was 3. And then use your left arrow or click to get out of that. And then type your function. I can just type f of x here because I already have it defined above. And then dx, put your bookend, and boom, it got it for you, 12. What? So when we get to word problems, it's going to be more important to set up your integral. You're going to have to read the word problem and figure out how to set it up, but then just use technology to get the answer. Saves you a lot of time. And if I didn't have that function already defined up there, if I was typing in a trinomial, I'd have to be careful to put it in parentheses. So let me go ahead and type this in the way it would look. I'd have to put my entire function in parentheses there to show that whole trinomial is one single function. But look at that, boom. It's pretty cool. Any questions on the technology for calculating the area under this curve? I kind of feel like I just took all the fun away from this, right? I mean, technology just boom does it for us. Like, that's not fun. Or maybe it is, I don't know. I'm like sucking the fun out of calculus. Okay, any questions or comments before we continue on? Is everyone just like, I can't see any faces. It's so weird. Normally I can see the look of terror on your face, so I'll know, but like now I'm just imagining all of y'all are smiling. Oops, I shared the wrong thing. Give me one sec. I meant to share the notes again. Here we go. Application window. Not Desmos. Here it is. Okay. Okay, so let's look at, oh, there was all the technology. Let's look at what use substitution looks like with all this, right? Oh, cool. Belinda got it on her graphing calculator. Yeah, on the TI-84, it sets the notation up just like Desmos does. And it's so easy. If you have a TI-83, or even I guess only the 84 Plus is the really nice one. But if you have like an older calculator, it's a little bit harder to type it in, but I can help. You have to do like more programming. But if that's the case, you can just use Desmos on the test. So, but I'm glad you got that, Belinda. Yay. Okay, so let's talk now about what use substitution will look like for this, okay? And remember, you'll have to do one of these by hand. So I'll probably give you one with use substitution, right? You got to make it worth our while here. So let's see what in the world this would look like. Okay, so 90% of the problem, maybe even 95% of the problem, is what you've been doing. So remember, you have to figure out what rule are you trying to reverse. Well, I see a fraction, right? So I'm thinking I'm probably going to have to reverse this rule here, my ln of x. So I'm going to write it out. To reverse this rule, I need a plain variable in the denominator. A plain variable with an exponent of 1. And right now I have a binomial in the denominator. So I'm like, whoa, that's not a plain variable. It's an x plus 1, not just an x. But it does have an understood exponent of 1, right? So we got that going for us. So if I wanted to, you don't have to write this down, but if I wanted to, that is a binomial to the first power. Oops. Uh-oh. There it goes. It is a binomial to the first power. So we have this exponent of 1 going for us, so that's good. But the plain variable, so that's how I know I need u substitution. So we're going to let u be the x plus 1. Okay, so right now it would look like this. Integral from 2 to 8, 1 over u, because I just, technically u to the first, right? But I just replaced that denominator with a u. I replaced all this with a u, and then I have a dx. Uh-oh. That's, my variables don't match. So then I have to come over here and take the derivative of u with respect to x. So let's go ahead and do that part. Oops. Let me move this over here a little bit. Okay, so the derivative of u with respect to x is just going to be 1 plus 0. That's just 1. Then I move my dx to the other side. So all this is familiar. That 1 is understood there. You don't really need it, right? So du is just equal to dx. So whenever I see this dx, I can swap it out directly for a du. So this dx right here swaps out directly for a du. Okay, so I got this. Nothing new here. This is all stuff you've been doing. Now, here's the deal with this. We're going to use we're set up to do our rule, right? We're set up to do the rule. Let's just double check. Do I have 1 over a plain variable? Yes. Is the exponent an understood 1? Yes. Can I use this rule? Yes. So let's use the rule. So that would be the natural log of u. And instead of a plus c, I have these rules. Now, careful here. When I write this out, remember that lower limit and upper limit were when I had x's involved. So when I have to do u substitution, I'm going to write in x equals on those right from the beginning to remind myself these are in terms of x. And if you've taken calculus before, there's something really slick you can do with those, but I'm going to do the way our textbook does it. So I'm just writing those x equals to remind myself I cannot plug these in yet. I can't plug those in yet because it's still in terms of u. We need it to be in terms of x. So you have to do that step of unsubstituting, remember? So you need to unsubstitute. We need to unsub the u equals x plus 1. So let's go ahead and do that. Now we can plug them in because they're x's and we have x's in our argument. Now I can plug in the 8 and I can plug in the 2 and I can subtract them. So let's go ahead and do that. So that would be natural log of 8 plus 1 minus natural log of 2 plus 1. So one time I plugged in the 8, one time I plugged in the 2, and then I subtracted them because that's my rule. And on this, I would be happy just for you to leave it as natural log of 9 minus natural log of 3. I think that's what MyMathLab wants. Or if not, it's going to tell you to, like in fine print, remember how it tells you to like round? If I type this in my calculator, I'm going to get like a yucky decimal. So where you enter it's going to say like round to the nearest 10th or something like that. So be really careful. If it doesn't tell you to round, you're going to enter this exact answer. But if it does tell you to round, you have to follow those rules on MyMathLab. I would just stop here because that's pretty, I don't know. Let's find the decimal. Let me just type that in my calculator. Natural log of 9 minus natural log of 3. So I got approximately 1 if I round to the nearest 10th, it would be 1.1 because it's 1.0986, blah, 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 blah. I don't know. Just be really careful on MyMathLab to read that fine print. And if you have any questions, you just shoot me and ask the instructor. So far, the only new step is plugging in these numbers and subtracting. That's it. That's the only new step. How are you feeling on this u substitution here? Any questions? Okay, I think we only have, oh God, we have 3 problems left. We can totally do this. Oh, I heard a little chime. Yeah, so yes, Anastasia, I would just leave it like this on the test. I won't ask you to round or anything, just leave it there. But if you do go a step further, I'll count it right. And if you do round it, I'll count it right. But yeah, I would leave it starred. Okay, now we have 3 word problems and we only have about 15 minutes and you're probably thinking, there's no way we're going to do this. But remember, with word problems, you can use technology. All you have to do is set up the integrals. So for word problems, we're going to set up the integral. Then use technology. Yay, technology. Going to set up the integral and use technology. Okay, so here we go. Let's read the problem. Let's set up an integral, and then we're going to use technology. So this problem says a company manufactures X HD TVs per month. The monthly marginal profit in dollars is given by this function. Okay, and X is restricted between 0 TVs per month and 4,000 TVs per month. Okay, the company is currently manufacturing 1,500 HEDVs per month, but is planning to increase production. Find the change in the monthly profit if monthly production increases to 1,600 DVDs. Okay. So since we're in this section, you know, oh, I'm going to do an integral. I'm going to work backwards, right? So basically, if you're wanting, the wording in this kind of throws students off sometimes when it's out of context, when we haven't just done integrals a million times, because we see this word change, right? And we're like, ooh, change. Is that a derivative? Change in monthly profit? So the monthly profit is given by P of X. That's your monthly profit. The P prime is your marginal monthly profit. So if I want to find the change in this profit, I would have to know what 1,600 DVDs would be, and then I would have to know what 1,500 DVDs, HD TVs would be, and then I would have to subtract them, right? Like, that's how I would find the change in the profit. I need to know the profit function, and then I would have to plug in numbers and subtract it to see how it changed over time. And that's what our integral does for us. Taking the integral finds the original profit function, plugging in the limits of integration, and then subtracting them does this calculation. So all we need to do is this. We just need to take our marginal profit, find the integral, and then go from 1,500 to 1,600, and it'll do this calculation, because what that's going to do is it's going to give you your original function back, and then you're going to go from 1,500 to 1,600, which is exactly what we would want to do. But technology is going to do it for us. So all I need to see for you to get credit for this is this problem right here. I'm going to write it in red. This is what I would need to see. 1,500 to 1,600. Then put your P prime rule in there. Put it in parentheses because it's a binomial. Dx, and then the answer. And then interpret it, right? Because it's a word problem. So I'm going to go to Desmos. I'm going to type this in. And then see what the answer is, and then interpret it. By interpret, I mean just use correct units, right? So I'm going to go to Desmos, plug that in. See how it just takes all the fun out of it? 16, 15, minus 0.1 x from 15 to 16. Okay, let's go type that in. Okay, so let's type in our function, or integral. So I'm just going to go straight down to my keyboard. Then again, you go to miscellaneous menu and go to your integral. And I'm going from 1,500 to 1,600. And then in parentheses, it's 165 minus 0.1 dx. And even though I can't see it on the graph, it's calculated that integral for me. And if you want to do it by hand, you totally can. Oh, go ahead.
I forgot the X.
Oh, I forgot the X?
Yeah,
Okay, thank you, thank you. Oh, I did. Holy smokes. That's better. Oh, that would have been a lot of TVs. Okay, luckily when I went to interpret my answer, if I had kept that, and I went to interpret my answer, I'd be like, okay, my domain only went from 0 to 4,000. So that number I got was ridiculous. So I could have caught that, but thank you. Don't you wish we took group tests? Okay, 1,000. So the answer is 1,000. So then I'd go back to my paper and write 1,000 and then put correct units on it to get full credit. So I'm going to come back to my paper now. Here we go. So I'd write in 1,000. Okay, and then find the monthly change in profit. So what was my output? Remember, this is an output. We create an output. The profit was just in normal dollars. So I'm going to have normal dollars. And since it's positive, it's an increase. So if I go to interpret this, I would say the profit would increase. Or you can even say under these conditions, so you don't have to rewrite all that. So I don't have to say going from 1,500 HD TVDs to 1,600 would change the profit. I just say under these conditions, monthly profit would increase, because it's positive, by $1,000. Not bad. Not horrible with technology. Okay, let's try another one. If there aren't any questions here. No, let's try another one. Okay, now the next two have some formulas that will be given to you on the test. You just have to know how to use them. They're business concepts, so they'll totally be given to you. One's called useful life, and the other one is going to be average value. But again, you're just going to set up an integral, and then we're going to use technology. So this first one is this idea of useful life. The useful life of a product. When you buy something like a copy machine, you know, there's expenses to a copy machine. It starts to break down. You need to repair it. So at some point, the business has to decide when is its useful life done, right? So this idea of useful life, you'll see in some of your business classes later on. But here's our problem. It says, an amusement company maintains records for each video game installed in an arcade. Suppose that C of T and R of T represent the total accumulated costs and revenues in thousands of dollars, respectively, T years after the game has been installed. So I'm inputting time in years after the game was introduced or installed, and I can calculate total cost over that time, and I can calculate total revenue over that time. And then we're being given these two marginal cost and marginal revenue functions. So these would be given, like some computer would generate these for you, right? You'd look at data over a long period of time and it would generate these functions for you. So I have my marginal costs over T years and my marginal revenue. Now, the useful life is when the marginal cost, the change in the costs, and the change in the revenue equalize each other. That's a useful life. So I just need to figure this out. Like, what in the world? How would I find the useful life of this game to the nearest year? So if I'm just being asked to find useful life, that's it. I'm going to use the useful life function, or this formula, sorry. So let's write out this formula. So for A, my useful life formula says you just set marginal cost equal to marginal revenue. Okay. So my marginal cost was a 2. My marginal revenue is this guy. And the useful life is how long it's useful for, how long it's worth keeping, right? So I need to find T. So I need to solve for T. So we're just going to do some algebra to solve for T here. This is not calculus. No calculus is happening right now. Absolutely no calculus. This is algebra. So my T is trapped up here in an exponent. Here's my T. It's trapped in an exponent. The exponent is trapped in an exponential. So the first thing I need to do is get that exponential alone. So I'm going to divide both sides by 9. And you're going to get a yucky decimal. So I suggest just keep it 2/9 for right now so you don't have to round. If you round too much while you're calculating, it can throw your answer off depending on how long a time interval is passing. So just keep it 2/9 right now. And then you have to think back, put your algebra hat on. If your variable is trapped in an exponent, so this is an exponential function, how do you get the exponent down? What undoes exponentials? Yeah, logs, right? So I can take the log of both sides if I want. Or I can take the natural log of both sides. And I'm going to choose natural log because I have a base e here. But when I do that, we have a rule in algebra that says you can drop that exponent down to the front. So I would have natural log of 2/9. And I'm going to put that fraction in parentheses just to make sure my calculator knows that's 2/9 is my argument. And then I can drop that exponent down to the front and I would have natural log of e. And if you know from algebra, natural log of e is just 1. Or you could just type that in your calculator real quick. Type in natural log of e, and when you press enter, it's going to give you 1. That's why I used natural log instead of log log. Log would have worked, it just you would have had more decimal, like more numbers to keep track of. If I use natural log of e just goes to 1. And then I'm almost done. I can get that t alone. Right now it's being multiplied by a decimal, so I just need to divide by a decimal. That'll divide off. I'll finally get my time. And so I'm just going to type all this into my calculator very carefully, and let's see what we get. Okay. I got approximately 3.00815, so on. So to the nearest year, that would be approximately 3 years. Approximately 3 years. Okay, any questions how I got 3 years? Show me a status so I'll know how you're feeling with the 3 years there. How are you feeling with how I got 3 years? I just use the formula that'll be provided for me on my test. Then I use some algebra. I had to remember that exponentials and logs undo each other. Okay, well, ready or not, let's move on to the calculus step. Okay, so now for B is asking me to find the total profit. Total profit. Total profit. Let me write that down. I need to know total profit. Total profit during the useful life. So that means, so during the useful life, that's going to be from year 0 to year 3, because that's how long it's useful, right? And you have to remember profit. Let me shrink all this so I can see my, how do you find profit? This is business, not calculus. Just how do you find profit? Isn't profit just all the money coming in minus all the money coming out? Profit is revenue minus costs. It's all the money coming in minus all the money coming out. So I can find revenue if I take the integral of r prime. And I can find cost if I take the integral of c prime. And I can find profit if I take the, the integral of p prime. Like, you could just work backwards. So I can combine these. I know r prime, I know c prime. So if I want to find my profit, I'm just going to take the integral of r prime minus c prime. So I'm just going to take the integral of my r prime function, which was 9e to the 0.05t, minus the cost function, which was a 2. There we go. And I'm going to write it as one big integral because we get to use technology. I don't have to do it by hand. So I'm just going to use technology to get this. So if I was doing it by hand, I might want to split it into 2. Technology. But we're just using, I'm just going to straight up put this in Desmos. Except I forgot one thing. If I need my limits of integration. So I need to go from year 0 to year 3. So I'm going to input a 0 for my lower limit of integration and a 3 for my upper. And if I put that on my calculator, it'll straight up give me the total profit. Because remember, this is like adding up all those rectangles. It's totaling it up. So total profit is adding up all these little rectangles. So let's just put that in our calculator. We'll get the answer, and then we'll stop here for today. Average value is super easy, so I'll do that next class. I can make a video for it, and I'll post it for over the weekend because it's way easier than this problem. Okay, so let's put this in our technology super fast. See what we get. I'm actually going to put it in, well, here. Let's see. Oops. Is it sharing my screen? There it goes. Okay. So I would just type this in super duper duper fast. So I'm going to go from 0 to 3. And then it was 9e to the negative 0.1t minus 2. I did that off memory. Was that correct?
It should be to the negative 0.5t.
Oh, the negative 0.5t? Okay. Sorry, I was doing that off memory. So yeah, look how easily that calculates it. I mean, so the total profit would be not a 7.98, but I think it said in thousands of dollars, right? Or was it millions? It wasn't just normal dollars. If you only made $7 of profit over the useful life, you messed up, right? Like you're not making good business decisions. So let me come back over here real quick. So the answer, the P, came out to be approximately 7.98. But let me go read what my output should be. Yeah, in thousands of dollars. So this would be dollars, and this would be thousands. Okay, so I'll make a video for average value. Y'all, average value is so easy because it just straight up gives you the formula. I mean, this will be given to you on the test. You just literally plug numbers in and put it into Desmos. But I want to talk about it a little bit more next class because I don't want to rush through it. But I'll put a video if you want to get a head start on your homework. But we'll do this problem in class, and then we'll start section 6.1 on Tuesday. So yeah, y'all are good to go. If you're taking a retest, I'll see you either Friday or Monday. And if not, I will see you on Tuesday. And I'll hang around if you have questions.